Are you in a different room today? The mic quality is a bit different. Oh no, maybe I actually have the wrong mic turned on. Let me verify I've got the right mic set up. Default microphone. Yes, I do have the wrong mic. Give me a second. There, is that better? Much better. Okie dokie. Yeah, I had the wrong mic turned on. My goodness, I'm a mess. Tough loss for the Bills this weekend. Don't even. Okie dokie. Last time we were finishing up talking about like pointers and dereferencing and getting the address of with that address of operator, the ampersand. And yeah, let's continue on with that. We were actually basically at the very end of that. For some strange reason, I'm certain I set the names to be anonymous, but it's not working, so that's funny. Okay, no, we don't want to raise. We want the end of pointers. Okay. This was ruin everything. We finished with this. Okay, one last quick test. So I've got three variables here. A, which is an integer, B, which is an integer pointer, and then C, which is an integer pointer pointer. And this all makes sense because, here, let me draw, and I actually have a stylus here. Let's see if I can use this properly. Okay, so we've got A. Oh, no, that's wrong. Ignore all this. We have this box A, which has the value 5 in it. Then we have a box called B. So this is an integer. But in here, we've got the arrow that gets us to A. And then in C, we have another variable, I'm just drawing as a box, of course, which is a pointer to something that is a pointer to an integer. This is weird, and I'm doing this in this example, and I realize this example is fairly contrived, but I'm doing this for the sake of, like, we can do this. We're allowed to do this, and that's why we have int star star. Well, because, well, this is a pointer, and then what's the type of thing in this box? Well, it's a pointer to an integer. So that's, like, this all checks out. Oh, also, another note. If you see me bouncing around, it's because I switched from a chair to one of those exercise balls, so don't be weirded out by that. So in this example, we print out A, we should see 5, right? Print out B, we should see whatever the memory address is of this. So this might be something like OX11112, or I don't know. C should be the memory address of this. So this would be like OX17E450. I don't know. I'm making these numbers up. But the point is, it's just a memory address. And then I could ask, well, what's the address of C? And that would be, so this would be the contents of in here. But then this box, of course, is in RAM somewhere. So the address of C, let's see if I can draw an ampersand. Not too bad. The address of C would be something like OX44726. Like, these numbers are arbitrary. I'm making them up. The operating system decides. But these are just all memory addresses, right? So this memory address I said was like, I don't know, 11112. So A is in location 11112. B is in location 17E450. And then C is stored at 44726. Again, completely arbitrary. Now, here's a bit of a funny quiz. What would happen if we say this? Because we're using the stars here next to the variable name. And that means dereference. So if we take C, which is this, and we see, okay, star C, well, that gets us to the contents of this box. And then if we say star this memory address, it'll get us to the contents of this box. So we should see a 5 printed out. What's going on here? Yeah. Now, here's the real test. In fact, let me see if I can change. This is the first time I'm using the stylus, so I'm not very good at it. All right, well, I suck, but we'll see. What's going on here? If you can't see, that's an asterisk or an ampersand A. What does that mean? Take a second and think about what I'm asking C++ to tell me. Now, don't type in the chat. I don't want anyone typing in the chat. I want people to take a second to actually think about this. think about what that means. I'll give you a minute because this is critical. Remember, ampersand address of. Remember, I had it that this was like memory address 0x11112. Again, completely arbitrary. Now, you may be slightly tempted to say, well, okay, the address of is like this, right? But it's not. And here's what we're asking. We're saying, okay, the ampersand A means where in RAM A is. And I said, for example, it is 0x11112. And I realize I'm really messy, bear with me. But this would tell me, like ampersand A would give me 0x11112. And then I ask, okay, what's the memory address of that? But 0x11112 doesn't have a memory address. Ampersand A is just, what's the address of A? And that's just like your street number. Imagine like you live on your street, right? Maybe you live on like 14 Highland, okay? And I look at your house and go, okay, you're in there, but what's your address? And I look, oh, it's 14. And then if I ask, but what's the address of 14? That question doesn't make any sense at all. That question, like, there isn't an address of address 14. It's just address 14. That doesn't make any sense. So here, asking the address of twice in a row like that makes no sense computationally. In fact, and I don't think I have Visual Studio open, which is too bad, but if we type that in, it's going to say like, yeah, this isn't a thing. This doesn't make any sense. Okie dokie. Do I want annotations? No. So, are there any questions about that before we move on to talk about static arrays? We're all good? Okie dokie. I'll assume we're all good then, in that case. So, I'm actually going to open up Visual Studio right now to show you. And we'll get a sense of just how Visual Studio is being helpful. Okay, class 1. My computer's painfully slow. I know, I complain about it every time. Let's move this there. And I should probably share my screen again because now you'll see what I'm doing. Oh. Don't crash, please. Don't crash. All right, well, in the meantime, while we await Visual Studio to actually open up, I'll start talking about static arrays. And I can just jump over here to see. Oh, no, okay, we're good. Actually, so let's just do this real quick. So if I have something like int a equals 5, if I say address of, a, and I run this, it's going to be fine. But if I say address of, what are we going to get? Yeah, see, look, what is it telling us? Expected an expression. Well, I mean, that error is not overly helpful in saying what's wrong here, but we can't do this. You can't get the address of an address unless that address is stored in a memory location, because then that address would have an address. But when we have just an address, it's not stored anywhere. There's no address there. So it doesn't make sense. Okay. Static arrays. I'm emphasizing static for an important reason. These arrays are different than dynamic arrays. Static arrays are awesome and horrible at the same time. They're really good at what they're good at, and they're not very good at what they're not good at. And we're going to talk about static ones first because they're a little simpler, and then we're going to move on to dynamic. For those of you coming from Python who have experience with the lists are going to be more like dynamic arrays, but the lists really aren't that much like the dynamic arrays because they're a lot more interesting and powerful, but static arrays. So what are we going to do? We're going to see how to make static arrays in C++, see how to use static arrays, see how pointers work with arrays, and see how arrays, or at least the static arrays, are very limited. Yeah. So, and then how are we going to pass these things to functions? Okay. So static array means that its size is known and it's not going to change. We say something like this in our code, int foo square brackets 5. That tells the computer we're going to take a chunk of contiguous RAM that's ready to hold 5 integers. I mean, when it's created, there's just going to be garbage in these memory addresses. But all it's doing is saying, okay, computer, go find a chunk of RAM that's big enough to hold 5 integers, and we're good to go. It's setting it up. We haven't assigned any value to it yet. We've just initialized this array. So here we go, int, and we all learned from the lab that the integers are going to be 4 bytes or 32 bits, right? 8, 16, 32, yep. So how many ints can fit in here? Well, 5. 1, 2, 3, 4, 5. But of course we start counting at 0 because we like counting at 0, and we'll see a big reason why we count from 0 here in a moment. But this is 0 is a location, 1 is location, 2 is location, 3 is location, and 4 is a location that we can store value. So 0, 1, 2, 3, 4, that gives us a total of 5 spots. How many ints are there currently in there? Well, this is kind of an ambiguous question because technically we have not put any integers in there. There's no integers in there. However, when we assign a chunk of RAM, the computers aren't RAM, when it's not used anymore, there's no process in the computer that goes through and sets all the zeros and ones in those RAM addresses to all zeros. That doesn't happen. There's going to be a bunch of garbage in those chunks of RAM, a bunch of zeros and ones that were used for something else at a point in time, but they're not used anymore. So the computer doesn't need to clear it out. All the computer needs to know is, okay, this chunk of RAM here, I'm not using it anymore. There's zeros and ones in it, but when I need it, I can overwrite those things, doesn't matter. But in this situation, when I open this up and I create this chunk of RAM for 5 integers, there's still going to be a bunch of zeros and ones in there. And I can decode these zeros and ones as an integer. So there's 2 answers to this question. The answer is, well, currently I didn't put any integers in there. So there are no integers in there. But we can decode the series of zeros and ones in those memory addresses, or those 4 bytes of memory addresses, and decode it as an integer, FYI. Kind of depends how we think of it, yeah. So if I do something like this, default values, well, if I go along and print this out, if I write this, I declare a variable that's an integer array of size 5, and I do my for loop from 0 to less than 5, I++, and then just print out whatever is in there. If we're running C++ in debug mode and it's Visual Studio C++, it does kind of give us, and we actually discovered this in the lab the other day, because I always forget every year what this is exactly. For Visual Studio, this is kind of like a special value, and it's actually in hexadecimal, it's CCCCC, a bunch of C's, but when you decode that as a base 10 number, it's negative 858,993,460. This is kind of like a default value that C++ is giving us, but only for debugging purposes. If we didn't run it in debug mode and we didn't, and perhaps we were using a different C++ compiler like your GCC or something, then this would just be a whole bunch of garbage. In fact, I'll show you an example of this here. And by the way, you might remember in Python, if I try to go past the end of a list, Python says oh, index out of bounds, right? If you're a Java programmer, you've seen exception, array index out of bounds all the time. It happens all the time. That happens when you've got an array of size 5, for example, and you're trying to access something at index 20. It doesn't exist, right? We only have memory at indices 0 through 4. If I try to access index 5, that doesn't make sense. But in C++, it'll let you do it. Here's what happens. I initialize this variable, foo. It's a static integer array of size 5. And I told it to print out what's in memory address 0 through 9. Printed it out. And we see in the first 6 spots, we've got the garbage. But then suddenly, I'm getting more garbage. This is a good example of just the zeros and ones that happen to be in that chunk of RAM that was wherever this array is stored in RAM. plus however far I have to go to store another integer. There's just a bunch of zeros and ones in there, and then the computer's decoding those zeros and ones as an integer, and this is the integer. Here's another one. I guess here we get 1. Wow, isn't that, how lucky are we? But the point is, 1, C++ really, technically, it doesn't initialize a variable for you with any special values. In asterisk, there's like debugging values that it can use. So really, we have to be careful and just be aware that, you know, if we ever want to use this array and we feel like we should be initializing it to something, maybe all zeros, we have to do that ourselves. We have to go through the array and put the value 0 in there. The other thing to take note of here is that C++ has no issue with you going outside the bounds of the length of the array. This array has indices 0 through 4. And it is fine by me saying, okay, tell me what's at foo location 7. And it's going to say, okay, 0, 1, 2, 3, 4, 5, 6, 7. Okay, it's 120,000. Wait, no, 1,200,000, no, 12,001,998. But I didn't create that. Like I didn't say, here is your 5 long thing. C++ is saying like, oh, okay, yeah, you want to go to that index 7? It just carries on down the memory addresses and just tells you what's in there, even though you really shouldn't be doing that. But why? Well, because C++ assumes you know what you're doing, despite the fact that you probably almost definitely did not want to do this. All right, starting with values. Now, in those examples, I set it so like it didn't have any values in there, but I can write something like this, and not only will it create and go assign a chunk of RAM with the space for 5 integers, it will actually then assign them the values 5, 6, 7, 8, 9. What's the size of this array? Well, it's 5. How many things are in there? 5. What's the contents of the array? 5, 6, 7, 8, 9. In this particular example, you don't actually need to say the 5 because it's smart enough to go, well, you put 5 things in here, so it's going to be size 5. Just FYI. But, you know, it's never bad practice, I guess, to maybe be more explicit. But then again, I guess if you come along and you want to make this size 6, all you have to do is add another number and then you don't need to change anything there. Whatever. It's just a quick little syntax quirk. Yeah. In this case, what's the size of this array? Well, it's 3, right? There's only 3 things there. Well, no, it's still 5, but there's only I only put 3 things in there. So if I were to print this out, I would see, I don't know why that printed funny, but I would see 5, 6, 7, and then I don't really know what's in the next 2 locations because I didn't assign those values. FYI. By the way, if you're thinking, oh man, I got to remember all this, you know what? I would never remember this. Every year I look at this and go like, oh, okay, that you can do that. And I never, I don't do that this way. I can imagine there would be a time in my life where maybe coding something like this makes sense for me. But in general, you wouldn't typically do it this way. I'm just showing you. Different types of arrays. Well, okay, we can have an integer array, a character array. Again, mind the fact that these are single quotes, not double quotes. A Boolean array, a double array. I'm certain I said it earlier, but I'll say it again. Double is, we'll use the word double to mean float. Now, here's the funny thing. In Python, you were okay to mix types in your list. You can have an integer, a float, a character, and a Boolean in your list. It was fine with that. But it's not fine in C++. Although, you'll notice, and we did cover this in the lab last week, you'll notice that, I told C++ it's an integer array. So if we were to go out and print all this, it's going to assume that we are to decode the zeros and ones in those 4 bytes of consecutive RAM. Well, okay, 4 sets of 4 bytes because we've got 0, 1, 2, 3 here. 4 bytes, 4 chunks of 4 bytes of consecutive RAM. It's going to assume that it's to decode all those zeros and ones as integers. So it looks like it's doing that. 40, well, 40 is just an integer. 40.1, well, it's going to assume that's an integer though. So just, okay, well, it's 40. A, well, we did see that the zeros and ones that mean in binary 97 mean the letter A if we decode it as a character, and then true is just not 0, so 1. So it's assuming that it's to decode all of these things, even though they're different types here where we set them, it's going to assume and be like, no, 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 those are integers. It's fine. So you got to be careful. This could bite you. Oh, I hear, what do we got here? Why do we use doubles if they take up more room than floats? Don't worry about it. Just do it. We'll talk about that later. That's a bit of more of a question for, that might be something I go over in lab, but that's more of like an engineering kind of thing. And you'll learn a lot more about how floating point numbers are stored next year in another course. And it's rather complex. So you'll learn a lot about that later. So sorry, but at this stage, it's the magic code we use. I know. Here, we have to be careful though, because if we're decoding this as a character, well, the integer 40, I guess, is a open parenthesis, 40.1, well, it's a character, open parenthesis, A is A, and true is, well, I guess it doesn't really know how to decode that as a character. So if I were to do this, something funny is going to happen. Yeah, you might think this is cool, but chances are you really don't want to do this. Okay. Strings. This, no good. This won't work. C++ cannot interpret the contents of the array as strings. And it's because like strings are a lot more of a sophisticated structure and thing that we're going to store in RAM compared to things like integers, doubles, booleans, and characters. They're a little bit more complex, and the structure and how they're stored in RAM it's not going to work the same as the primitive types are. But we can do this. Although we're going to see hello, we're going to see world, and then it's probably going to crash or maybe give us a bunch of garbage. This is no good. We've created a string, or pardon me, an array of strings. It's size 2. It's got index 0, index 1. And then we're trying to print out indices 0 through 4, and it'll print out 0, it'll print out 1, and then we're just going to get a bunch of nonsense after. Did I hear? Okay. In accessing contents, well, this is going to be just like Python indexing lists, right? So foo at location 2 should be everybody 0, 1, 2, the 7, right? So I've hard coded the 2 in here, but it could also be like oh, okay, foo at location 2 is now set to 77, fine. Foo and index is set to 88, so I guess this becomes 77, this becomes 88. Foo at, oh my goodness, what am I doing here? Foo at location 1, okay, so 6, minus 2, that's 4, so 0, 1, 2, 3, 4 is set to 99. Okay, so if we run this, we will see 5, 6, 77, 88, 99. This example right here, very contrived. I mean, it's nonsense, but I can do it. Now, what do we got here? Okay. So what's going to happen in this situation? Well, it's going to work. I created an array of size 0, okay, 1, 2, 3, 4, 5. We've got 5, 6, 7, 8, 9. But then I'm saying, okay, foo at index 5, you're 0. Foo at index 6, you're 111, and foo at index 7, you're 222. But like, this is weird, right? Because, well, there really shouldn't be an index 5, 6, and 7. C++ will let you do it, though. We can access it and assign those values. But this all comes down to the fact that, and we're going to see this very shortly, arrays are really just pointers that we're doing some like memory address arithmetic on. For C++, do we have to start the index counting at 0 in Python? Yes. Yes, 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 yes. And we're going to see why computer scientists like to start counting at 0. We should see that in this lecture. Most programming languages are going to start counting at 0. Programming languages that start counting at 1, with one exception, maybe 2 exceptions, are all garbage. we count it from 0 for a very good reason. Okay, multi-dimensional arrays. We can have arrays of arrays. So in this case, foo, it's a 5 by 2 array. We've got 1, 2, 3, 4, 5 things in it, and each one of those is size 2. So is the adding to the, okay, so is this adding to array? So if that would happen, if we tried to add to the array, but the next memory spot was taken up already. Okay, so yeah, you bring up a good point. Really, we're just doing like pointer arithmetic with arrays. It's like it's like what we did in last week's lab, where you've got a memory address and then you add 1 to it. I mean, C++ got mad at us when we were doing, or pardon me, Visual Studio got mad at us when we did that, but that was because Visual Studio was just being helpful, and also because we were playing around with like an integer. Once we're dealing with arrays, it's like, yeah, okay, just add whatever you want to these values. If, and like, given that we've got like a bajillion memory addresses and the operating system's gonna assign this stuff for us, if we happened to do it in such a way that we made an array of size 5. In fact, here, I'm gonna go back and draw. Pen. I gotta get practice with my stylus here. So think of our RAM like this, okay? Forgive me. Okay, and then this is where our array starts. So I've got 5 in this chunk of RAM. I realize this is like 4 bytes long, but I'm just going to draw it this way for simplicity. 5, 6, 7, 8, 9. Okay, so this is like this. And by the way, okay, I can give you a spoiler right now. This pointer, this array starts at some memory address, right? Let's say it's OX 100. Whatever, a simple number. This is going to be OX, like 5 is at the start of the array plus 0. 6 is at the start of the array, the pointer, plus 1, which we know when you add 1 to a pointer to integers, it actually adds 4, but 7 is at this index plus 2. So you'll see that the array indices, like this, they're actually like offsets. So foo at 0, which should be 5, I mean, that is at this memory address plus 0. So we get the 5. Anyways, here's our array. We're happy with this. This is where it ends. But if we just so happen to have a very super special variable called super special, that just so happened, okay, secret to the universe. Pretend that's what that says, secret to the universe. If we are storing this in this memory address and the operating system just so happens to decide that, oh, we're going to put it at memory address, whatever this is, plus enough room for all these integers, and we decide to store it here, as soon as we write this line of code, we obliterate what is in this memory address. And then super special, it's now corrupt. We've lost it. Whatever that value is, whatever the secret to the universe is, it's gone forever. We've obliterated it. So, hopefully that answers your question, Duncan. Oh, too far. All right. Yeah, so a 2D one. Oh, come on. Let me draw again. So you'll see, I mean, there are 5 things in here. 1, 2, 3, 4, 5. But each one of them has 2 things in it, right? 1, 2. Whoop. 1, 2, 1, 2, and so on. So that's why it's 5 by 2. So the length is 5. And then inside of it, we have integer arrays of size 2. If I say foo at location 10 set to 22, well, what would that mean? Well, that would be, okay, this right here. Let me change colors. Green. This right here is 0. This right here is 1. This right here, 2. 3, 4. So we see foo at 1. That gets us to this one here. But what is this? Well, this is an array. So this array inside here, I'm going to change colors again, I guess. If I can. Oh, no. Where'd I go? Where was it? Here? Yes. And I don't know, purple. This one here, that's 0. And this one here, that's 1. So location 10 is 1, 0. So it's this 2. And we're setting it to 22. So if we were to run this code, we should see this. Huzzah, we're happy, yay. You can do this. I mean, don't. But you could, if you needed this, you could do it. This is A-okay. And the question I have for you now is, how many dimensions does this have? Well, we've got, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. I guess this is a 9-dimensional array. We have arrays of 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 arrays. Why? Because I can. All right, now as function parameters. It's not uncommon that we're going to want to pass an array to a function. So here's how you do it. You know, here I'm saying, well, this is an integer called toPrint, but because it's got these boxes here, like the square brackets, we know it's an integer array called toPrint. And then here we've got a variable called length because we can't, unlike other languages, we can never ask a static array or a dynamic array how big you are. We have to kind of know this already. So this function here will take an array and it'll know how big it is, and then it'll loop forever how big it is to print out the contents. Great. And then down here, I've made an array of size 0, 1, 2, 3, 4. Okay, so it's size 5. I print out an array and I have to tell it it's size 5. There. And this will all work just fine. All right, so arrays and pointers, they're going to act very similar. So here we go. If I print out an array, right? I'm not printing out an array at any index. There's no square brackets here. I'm saying, what's an array? This will actually print out the memory address of where the start of the array is stored. So I said the memory address the array is stored. This is actually not quite correct. Really what I mean is the memory address of the beginning of the array. So really this is a start of array, like I drew on one of the previous slides. So this is actually going to print out the memory address. We don't need to use the ampersand here because this here, because it knows it's an array, really it's just the pointer. So it's the memory address of where it's stored. Then the square brackets is like our pointer arithmetic. So do you think this, what do you think this will do? Okay. Maybe you can't really see it, but can I undo this? How do I, okay, erase. Take a second and think about this. What do you think this will do? It's not a trick question. What are the rules? Follow the rules and it'll all work out just fine. So take a second and think about this. And you know what? Instead of, sure, keep them for now. Instead of just guessing, let's see. I love that. I mean, we're spoiled in computer science. I can just, I guess I need to create it as well. Whenever we have a question like this, we can answer it just by running the code. Let's see what happens. So first, actually, I'm going to print out this. Okay. And then on the next line, I'm going to print out an array at index 0, but what's the address of that? And I mean, you'll see that if you just kind of like say what these things mean, it might kind of just tell you the answer. But let's see what happens. I'm building it. We'll give it a second. And then we'll run it. It's always the first build is so slow. There we go. Okay, what do we see? Whoop. Look at that. The same thing twice. The memory address twice. Why? Well, an array is the memory address of where the array starts. It is 0053F988. When I say an array at 0, that tells me what's in. That's like dereferencing the pointer plus 0. So it goes to the beginning, the value within this memory address. And then I say, okay, don't tell me the value, tell me the address of where it is. Well, that's just the memory address of where the array starts. It's kind of like redundant. Now, this here, like what would this mean? The address of the start of the array? Well, we saw at the end of last set of slides that this doesn't make any sense. If we're not like, this right here is just going to like give me, this operator returns the memory address. Oh, no. There. This right here tells me the memory address of where this is. That value's not stored anywhere. I guess, you know, it's kind of stored here, but I mean, what does this mean? Well, this is interesting. It looks like we actually can get the address of something. Well, look at that. How about that? That's interesting, isn't it? Oh, you'll also notice that when I run this, like this will always be different. Like it'll change, or it is very, 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 very likely this will be different every time I run it. And that's because, let's run it again. The computer is just arbitrarily deciding where we're going to store that in RAM. Okay. Any boops? Okay. Oh. Okay. Yes. So this is also valid code. Now, right here, like this is the same. These are like equivalent as far as the computer's concerned. We've got my array, int my array, open square bracket, close square bracket. We set it, we assign it some values at compile time. But I can create a pointer, an integer pointer, that is equal to my array, because my array is just the memory address of the start of an integer array. It's the same. It all checks out. In reality, this syntax with the square brackets is kind of just like a nicer, cleaner version of doing pointer arithmetic in a clean, simple way. Otherwise, we'd always have to be doing like my pointer plus something. And I think in this week's lab, we're actually doing a lot of just pointer arithmetic to essentially do the array indexing. Okay, so no need for the ampersand because my array already gets us to the memory address. And I can do this. I can do this. Look, it's not only that I can do pointer arithmetic on pointers to do indexing, I can do like the square bracket indexing on an integer pointer to index this thing. This all works. It's funny, isn't it? Here, indexing is just like dereferencing. This is it. So here's like a version of doing that with pointer arithmetic and dereferencing. I'm gonna say this one slowly. In fact, I'm gonna start drawing, I guess. Okay, whoop. All right, well, let's erase that. Okay. Okay, so what do we have here? Well, so this is memory address OX100. Why? Just because. And again, I know we have to add 4 bytes, but for simplicity, we'll just pretend this is 101, 102, 103, 104. This would be 105, but we don't really have access to that anyways. So we're just going to pretend we count by 1, just for simplicity. So I create the array of size 5, and I put 0, 1, 2, 3, 4, and then, I don't know what's in here. Who cares? And then I create another thing. So, okay, I create my array. I'm just going to draw that as my A, and really that's just a pointer to here, which really is just OX100, right? Then I say, okay, create an integer pointer called my pointer. Okay, my P. Well, that's equal to my array. Well, what's my array? Well, that's equal to OX100, which is effectively just a pointer to there. Great. So now we go down here from I 0 to 5. So it shows 0, 1, 2, 3, 4. What am I going to do? Well, there's a lot going on here, but all we're going to do is what the rules are. Break this down and what the rules are. There's no silver bullet trick here. It's what does the code say? Well, this says, okay, go to my pointer. Well, my pointer is OX100. Add I to it. Well, the first time through the loop, I is 0. So when I is equal to 0, we're going to print out my pointer, OX100, plus I, 0. So that's OX100. And we have the memory address, OX100. And again, by the way, when I say OX, that just means, okay, the address is in hexadecimal. So it's just address 100, we'll say. So we have the address 100, and then we put the star in front. Well, that means dereference. So it's not, well, memory address 100, it's what's in memory address 100. We should see 0 printed out. When I is equal to 1, we will see, okay, well, my pointer is OX100 plus I. Well, I is now 1. So my pointer plus 1, so that should be 101. Again, I know it would be 104 because we know it's 4 bytes, but simplicity, we'll just add 1. So what's in memory address 101? Because we do the dereference, so it's not memory address 101, it's what's in memory address 101. We print out the 1. And then so on for 2, I is equal to 2. Well, what's my pointer? Well, that's 100. What's 100 plus 2? 102. Dereference that. What's a memory address 102? It's the 2. So we print out the 2, and so on. Isn't that neat? You might hate this. I'm going to make you do this in the lab. Then after that, just index it normally. I'm just showing it to you because it gets you a little bit familiar with pointers and what arrays really are. Take my pointer, which is a memory address, pointer, add whatever I is to it, and then dereference that address. Okay. Pointer arithmetic is cool. At least I think so. You can do the same thing with my array. So here I was doing it with my pointer. Well, because my array is really just an integer pointer, I can still do the pointer arithmetic here too. So this is all interchangeable. This is not to lead you to confusion. In reality, don't do it this way. Don't do it this way. Don't do it this way. Give me an example of the way I want you to do it. Do it this way. This is the way you would want to do it. You create the variable, it's an integer thing called food, but it's an array, and then index it like that. That's the good way to do it. All these other things are just ways I'm showing you that you can do it. It's neat, it's cool, but we've got a cleaner way to do it, and we've invented this, like we created the syntax as humans for the square brackets because it just makes life a lot nicer and easier. Just got to keep an eye on the time. Yeah, okay. Void print array 2. So, I mean, this is the same thing. Like if we go back to this example here where I've got print array, it's an int to print square brackets. We can do this, int star to print, and this is going to work just fine. This is a-okay. So the only difference here, I mean, aside from the fact that the name is different, it's not print array, it's print array 2. The only difference here is we put the star next to the int to make it an integer pointer, and we didn't put the square brackets here. And it's still all going to work out. Now, if we said int star to print and then had the square brackets, what would that mean to the C++? Well, that would mean that we want like an integer pointer array, not an integer array. So we got to be careful. And then, all right, so remember this from last lecture. Some pointer, we get a pointer to X, a pointer to Y, and a pointer to Z. And then we say, okay, dereference Z and put into it the sum of the dereferenced X and Y. And then this right here, Z, or this function has a side effect. And the side effect is that it'll actually change what's in the contents of the variable C, which is kind of like not in this function. So this function has what we call a side effect. And this side effect is changing some information in RAM somewhere else with pointers, which is cool. So what's going to happen in this case? If I say int star an array at location 0 is 99, and this is what I'm doing here, like what's going to be printed out? Because, so this is a pointer, and in the previous example we had, okay, well the pointers ended up having side effects. Here we've got a pointer again. Is this going to have a side effect, or is this going to make a copy of the array, assign an array at location 0 to 99, and then as soon as this function finishes, that changes? Or is this going to have the side effect of making it so array at location 0 is 99, meaning we see 99, 3210? What's going to happen? Well, the best way to do this is to test it. I'm going to take this. I'm going to take this. Now, before I hit run, I want you to rationalize what's going to happen. There's no trick here. The only trick is, what does the code say? And what are the rules we know? So this is built. Come to a conclusion in your head what you're going to expect to see. Should I see printed out 43210, or should I see 993210? Okay, I'm going to hit run. Well, it turns out I only got, well, I guess I was only printing out array at 0. I got 99. And I heard a boop. What do we got? Just 99. Yeah, okay, that's what I meant. Would star array print out the whole array? No, star array would actually only print out the first, like, index 0. Yeah, that would be like the example of this when I was 0. So it's like my pointer plus 0 star. So here it's 99 because here this was a pointer to something somewhere else in RAM. This right here is how it works in like Python. When you have a list in Python, you are never passing Python, like you are never passing a function in Python, a list. You are only ever passing it a pointer to a list, which then when you make modifications to that list, it's going to make the modifications wherever it's pointing to. Now I wonder what's going to happen here. Are we going to see 99 or 4? Well, let's try. Spoiler. What? Copy. Okay. Why? Well, I mean, you might remember me just ranting about how, like, this right here, it's like, it's just a pointer. It's just an integer pointer to the start of the array, just like the int star was. So we should still see 99. Fantastic. And then do I have another example? Okay, yeah. And then how many slides do I have left? All right, I guess we'll stop here because we are out of time. And we'll pick up here next time, which is tomorrow. Otherwise, enjoy the rest of your day, and I'll see you all tomorrow.